Welcome back to ch205. In this video, I'll be talking about how we can solve a system of ordinary differential equations or initial value problems using numerical techniques that we learned so far, i.e. Euler's method, forward or backward difference, trapezoidal rule, or RK2 or RK4. Okay, so we're going to start with the generic form of a system of differential equations given in equation 5.3. This is, by the way, section 5.5 of the textbook on page 109. Imagine we have n differential equations. The first one goes like dy1 dt equals something like if one of the other, well, all other y functions, y1 through yn. And then dy2 dt is equal to f2, like different function. Okay, f2 as a function of y1 through yn again, all the way to dyn dt equals another function of y1 to yn. Of course, t is always involved because t is independent variable. For every equation, we have an initial condition, y1 at 0, y2 at 0, yn at 0. Okay, the goal is to find y1 through yn as a function of time. If you're confused what this means, I think the best would be look at one example. Let's say we have a reaction like this. A is converted into B and B is converted to C, but this is like forward and backward reaction. So B can also convert to A and C can convert to B. We have the reaction rates. That means A goes to B with this reaction rate K1, B goes to C with reaction K3, B goes to A with reaction K2, and C goes to B with reaction K4. Initially, we'll start, let's say, with all A species and no B and no C. And ask the question, what will be the concentration of A and B and C over time? I want to find the time distribution concentration of A and B and C, right? If the rate constants are given right here, then we have to solve some sort of differential equations to find A and B and C. So what would be the differential equation that governs the kinetics or the chemical reaction given in this picture? So this is how we can write. So we ask ourselves, what is the rate of change of A? The rate of change of A is dCA dt, right? This is the time derivative of concentration of A, and physically that means how fast the concentration of A is going to increase. Well, it's going to increase proportional to K2 because B is converted to A, so then it's going to be plus K2 times the concentration of B. The more B have, the more A we get because B is going to convert to A with the rate of K2. So it's going to be plus K2 times the concentration of CB. But at the same time, the concentration of A is going to go down because of rate K1, because A is converted into B. So it's going to be minus K1 times CA. Okay? So the forward goes with minus, and then the backward goes with plus. So minus K1 plus K2. This one is multiplied by the concentration of the species that is converted. And in the backward, you multiply K2 by the concentration of B because B is converted into A. Okay, so let's write the equation for B. Now B gets increased by K1 because K1 converts A to B, and by K4 because K4 converts C to B. So it should be a plus K1 plus K4. But then B is also decreasing because of K2 and K3, because K2 converts B to A and K3 converts B to C. Okay, the top one is the forward, the bottom one are the backward reaction rates. So it's going to be minus K2 minus K3, and every time we need to multiply the rates by the concentration of the species that is converting. Okay, so A is converted, so then it should be A is converted to B, so the concentration of B dCB dt, which is the rate of change of concentration of B, is going to be plus K1 times the A. Okay, And for K4 is going to be plus C4, and plus C, the concentration of C times K4. And for these two, it should be minus concentration of CV times K2, and minus concentration of B times K3. You can write the same thing for concentration of C, which goes up with Kc times Cb, right? And then minus K4 times Cc. That's what we have here. Okay, so now we have three differential equations. And the first one involves with Ca and Cb. This one involves with Ca, Cb, Cc, and so forth, right? And these are the initial conditions. So this is pretty much like the generic form we had here. Three equations, three initial conditions. You have to solve all of them at the same time. We cannot just go ahead and solve this one because this involves Cb, and if you don't know Cb, we cannot write the right-hand side. Same thing here. If you want to do this without looking at the other ones, we cannot do that because we don't know Ca, we don't know Cc. So these should be coupled and solved at the same time. Okay, so it's actually pretty much straightforward. What we do is, let's say we want to use forward Euler. We're going to apply forward Euler to the first equation, to the second, to the third, and then we solve them at the same time. And if you do that, then the equation would look something like this. So let's write the set of equations we get from Euler expansion. So this is going to be Ca, let's go this way. Okay, Ca at time n plus 1. This is a bit big, I'm going to make it smaller. Okay, so I'm expanding this using forward Euler. This is going to be the concentration at the current state. It should be Ca at time n plus dt times, this is going to be my F, right? So this should be evaluated at the current state, which means minus K1 times Ca at time n plus K2 times Cb time n. Okay, let me see if I move it over here. So this is the forward Euler expansion of the first equation, right? So this was discretized using Can minus 1 minus Can divided by dt, but I just did a cross product. I multiply both sides by dt and then move Can to the right side. Anyway, so this is exactly like the generic form we had for forward Euler, which is on equation, let me see, right here. Right this. Okay, yn plus 1 is equal to yn plus h, which is in this case dt, and then times the right hand side of the equation. Okay, so that's what we have here. We can do the same thing for the second equation and the third. So I write the second one, and then the third would be pretty much the same way. I don't think there's something special about the third. Alright, for the second one, we're going to get Cb at n plus 1 that's equal to Cb at time n plus dt times the right hand side at time n. So it's going to be minus, plus K1 times Ca at time n minus K2 times Cb at time n minus K3 times Cb at time n plus K4 times Cc at time n. So this is a bit long, so I have to move it over here. Alright, so we can go ahead and do the same thing with this third equation. Okay, let me just do that. Okay, so then Cc at time n plus 1 is going to be cc at time n plus dt times k3 times cb at time n minus k4 times cc at time n. Alright, so these are the set. You just go ahead and implement it in Spreadsheet. Very straightforward. So here's a spreadsheet, and here is the equation. You just put it side by side so we can easily compare. So this is the equation. This is the spreadsheet. I'm going to shrink this window a little bit, like that. Okay. So here's the spreadsheet. We're going to create the time. So we're going to start from time 0, and every time you can you can automate this sort of. The next time point would be previous time point plus dt, and I have dt over here. So it's going to be this blue cell plus the green. You can easily drag down. The initial condition for all CBC, CA, CB, CC is 1, right? And we have the rate constant over here in the top row. Okay, so let's look at the concentration of CA in the next time step is going to be the concentration in the previous step, right? Which is the blue cell plus dt. So here's dt, right? It's F2 times minus K1 CAN, minus K1 is the purple, times blue cell, which is CAN, plus K2 times CBN. So K2 is going to be the brown cell, and then times the concentration in the current cell of CB. So this is CB, the green cell right here. So this is it. You can do the same thing for CB. CB is going to be the previous CB, right? It's C3 plus DT times, this is K4, times the brown cell, which is CA, minus K2 times C3, which is this CB, right? Minus the orange cell, which is K3 times, again, CB, and then plus pink cell, which is K4, times D3, which is CC, and that's what it is. So you can go ahead and implement CC, right? So CC is going to be the CC is going to be the previous value, or the current one. This D is cell D3 plus DT times K3 times CB. So K3 is the purple cell times brown, which is CB, and then minus K4, which is this green cell, times CC. This is it. So we have it. The rest is just drag down. I'm going to clear this up, so you see that it really works. Okay, these are the initial condition. These are what I implemented, and then I'm going to highlight these 3 and drag down all the way to here. Here you go. And we can plot. So here's the concentration of, let's expand this. So green is the concentration of A, right, as a function of T. You can see over here, concentration against T. The red one is the CB, and the blue one is CC. So the concentration of A goes down, and A is converted into red and blue, which means B and C. So the equilibrium concentration would be, if you look at a longer time, maybe you can just drag this guy down further, maybe to 5 or 10, and time is equal to 5 or 10. Then you see that actually these level out, and that's exactly the equilibrium concentration, after which the concentration doesn't change, right? So that is the end concentration we get from this reaction. You can go ahead and implement a smaller DT, right? I have another tab. By the way, this spreadsheet is on Blackboard. You can go ahead and use it. So you can increase DT and see that how it affects the results. So here's with the smaller DT, which is 0.01, and I have another one which is 0.001. All right, and then there you go. So you can compare the result. I've put all of them together. So this is a comparison between DT.1 and DT.01. And we see that, let's compare 2 of them. I'm going to compare dark blue with pink. Sorry, dark blue with light blue. So these are the concentration at 2 different DT values, and we know that the solution becomes more accurate as you decrease your DT. So let's look at that. This is DT equals 0.01, and the dark blue, which is this guy, is the DT, is the concentration of A at DT equal 0.1.